bootstrapping. One of the very important concept we use the compiler design is bootstrapping. Okay. I hope any of you ask me any at least a small doubt in the between that will be definitely encouraging to our class. Okay. So we are writing a complicated compilers, okay, to handle a huge set of languages. In the first classes, I showed you a lot of compilers for the various programming languages. One more thing is definitely we are seeing lot of compilers are they are releasing version 1, version 2, version 3, version 4, like lot of latest versions are releasing. Each and every version we are handling so many difficult tasks. Okay, right. Everybody be careful. One thing I want to convey to you is no compiler can be designed in a overnight. Like a complex program or task is divided into small tasks or small programs, and we are handling those programs. The compiler also we can create a number of sub compilers, okay, to handle the complex tasks and can be uh, improved uh, task by task, okay, set of tasks. The thing is here we may not get the in the final compiler in the single stage. We may create compilers in the stage by stage, and the compilers whatever we created like object oriented programming, we can add one version of the compiler with another version of the compilers, or one part of the compiler handling the some task can be added with the other part of the compiler handling the other task. We can get the final compiler. Okay, right. So the main purpose of the compiler is to translate the source program into the target program. Okay, in translating the source program into the destination program or target program, we may assign a subtask to one part of the compiler, we may assign a subtask of one part of the program can be to the other compiler or operations. Okay. In this particular thing, a bootstrap can be used. Okay. The bootstrapping is nothing but a design process in the compiler. In particular, we call this bootstrapping is a process in which a simple language used to translate more complicated program, which in turn may handle more complicated programs. Okay, so we may use complicated programs. The complicated program compilation can be done by simple programs. Okay, simple process or simple programming languages. Okay, so we need not we need not incorporate all complicated tasks in the single program. We can handle this complicated programs, okay, using simple process, simple process of translating source into destination. These complicated programs can be further handled also to handle even more complicated programs. So that means we are not writing a program for the compiler to handle more complicated programs directly. Instead, first of all, we start with the simple translation. The simple translation programs may handle simple tasks. Then this developed small compiler program can handle more complicated programs by adding some more features or some more compiling parts. This is called as a bootstrapping. Starting with a simple program to handle more complicated program. In the intermediate, we can handle like functions. We can handle more number of compilers. Okay, right. Writing a compiler for high-level language is a complicated process. Definitely, we can't incorporate all complications in the single stroke. We need more time to write a compiler even from the scratch. That is the reason we can use available compiler translations, that whatever the already available, by using the available compilers, we can translate it to the more complicated compiler. So, in simple language is used to generate generally to target code into the up to some stages, in some stages. Then we can use that particular part of the compiler to translate it to the high-level language or complicated language. To do these operations, to give output of simple language compiler to the complicated language compiler or part of the compiler, the process we call as bootstrapping. Bootstrapping. Bootstrapping allows us to develop a compiler with a simple language to more complicated language. Simple language to more complicated language, right? So we can say bootstrapping is used to produce a self-hosting compiler. Self-hosting compiler. That means of the self-hosting compiler means a compiler which can take a language translated by the other compiler as input and generate more complicated program output as output. Okay. The self-hosting compiler is a type of compiler that compiler its own source code. Self-hosting compiler is a compiler that can host its own compiler. Self-hosting compiler is a compiler that can compile its own source code. So, this for the self-hosting compiler, we are identifying a compiler which can be
సార్
చెప్పమ్మా.
రిక్వెస్ట్ అంటే యాక్సెప్ట్ చేయండి సార్, వెయిటింగ్ లో ఉన్నారంట.
లేదు వెళ్ళిపోయాయి ఆల్రెడీ, ఇంకొకటే వచ్చింది ఇప్పుడు, లేటెస్ట్ గా 81 వచ్చింది, మిగతావన్నీ ఆల్రెడీ జాయిన్డ్. ఓకే,
అదే అది మెసేజ్
వెళ్ళిపోయి వచ్చేసే. ఓకే రైట్. ఇంకొక లాస్ట్ ఓన్లీ వన్ ఉంది, ఎవ్రీబడి జాయిన్డ్ ఆల్రెడీ. రైట్. In the self-hosting compiler is a type of compiler that compiles its own source code. Its own source code ante what it means is we are developing compilers in the stages. The previous stage, the output, this bootstrapping self-hosting compiler will take as input. Okay, we are attaching the compilers in such a fashion that self-hosting compiler can compile its own source code. That I am going to explain you in the coming slide. So the bootstrap compiler is used to compile the compiler. Okay, not source program now. The output coming from the previous compiler, okay, it takes as input. So we can call bootstrap compiler is used to compile the compiler. Okay. The compiler itself is nothing but a program which is translating source to destination program, okay, or source program to machine language target program, okay, high level language to machine language program. This bootstrap compiler, what it is used to compile the compiler. అంటే previous compiler నుంచి వచ్చిన output ని దీని ఇన్పుట్ గా తీసుకుని కంపైల్ చేస్తుంది కాబట్టి we can call the bootstrap compiler as compile the compiler. Okay, compile the compiler, and we can see this compiled compiler to compile everything else as well as the future version of the particular program itself. Okay, right. ఇది compile the compiler previous compiler నుంచి వచ్చిన output compile చేయడమే కాకుండా even we can supply it for the future versions of the compiler itself. Okay, right. Now we'll see some more things first, then I will show you 2 examples in how the bootstrap technique is using bootstrap technique considering the scenario అంటే ఓ sample case తీసుకుందాం. Okay. In the sample case, suppose the thing is we want to write a compiler. Generally, this taking a language from one compiler and generating to the other compiler, we call it is a cross compilers also. Okay, this bootstrapping process using the bootstrapping process, what are the compilers we are creating? We can call such compilers as cross compilers. Cross compilers అంటే ఒక కంపైలర్ కి ఇంకొక కంపైలర్ కి మధ్యలో కన్వర్ట్ చేసే ప్రోగ్రామ్ ఏదైతే ప్రాసెస్ ఏదైతే ఉంటుందో దాన్ని వీఆర్ కాలింగ్ as a cross compilers. Cross compilers. Okay, right. So the cross compilers using the bootstrap technique. So now we want to create a we want to create a program for writing a cross compiler for a language X అంటే సోర్స్ లాంగ్వేజ్ ఎక్స్. మన ఇన్పుట్ ప్రోగ్రామ్ ఏదైతే ఉందో దాన్ని వేర్ సోర్స్ లాంగ్వేజ్ అంటున్నాము. దట్ ద సోర్స్ లాంగ్వేజ్ ఈజ్ ఎక్స్. ఎక్స్ అనే ప్రోగ్రామింగ్ లాంగ్వేజ్ కి వీ వాంట్ టు డెవలప్ ఏ కంపైలర్. ఓకే, ఫర్ దిస్ the implementation language for the compiler is, let me say, Y, because any compiler, even say for example Java compiler is developed using the C language, then X is nothing but Java, Y is nothing but C language. The X is our source program. Okay, it can be C or Java or Python or any other programming language, but every programming language compiler is developed using one more simple programming language. Okay, that particular language let me call as Y. The target machine code, whatever we are generating, target machine code. Okay, target machine code means whatever the CPUs we are using, or whether it is a desktop or laptop or anything, every desktop laptop is containing microprocessor. We may call it as a third generation computer, fifth generation computer, okay, or Pentium 586, 686, 786, whatever the series it is, i3, i2, i5. Every compiler, every computer, we are having our own CPU. Okay, based on the CPU, we are identifying the computer. But be careful, every CPU, every that microprocessor is having its own instruction set. Whatever the target code we are generating in terms of zeros and ones for that particular CPU only, for that particular CPU only. Be careful. Okay, that particular language is called as target language, or let we call it as Z. That we call Z. So here it is involving three different languages. One is the source language X, another is implementation language Y, another is target language Z. Okay, right. That is one part. Now the thing is, if you are having then if existing compiler, okay, that implemented using the Y language is are executing on the machine Y, the existing compiler implementation language Y executing on machine M, that means the final machine language is called as M, and generates the code for that machine M only. Okay, we call it as YMM compiler or YMM machine compiler. Okay, first of all, we are taking the on the outside source language X, implementation language Y, our final target language Z. But once again, when come to the cross compilers, the intermediate compilers, as we are not directly generating the Z, before coming to the Z, we are doing lot of things. Before coming to the Z, we are doing lot of things. Okay, after getting the in the initial stage X value, okay, we are implementing the Y, that particular program. Now the thing is, the X, whatever the intermediate thing it is generating by the from the X is definitely to be understand by the Y only, the programming language. Whatever we are implementing, first of all, it is going to be recognized using the implementation language Y. So that existing compiler, whatever the thing is, it is going to be handled using the Y. The Y is going to be handled on the machine M, and finally generating the machine code for M. In the intermediate machines, intermediate machine codes also may be different. That is the thing. Okay, that is the reason The intermediate compilers, whatever we are identifying, we want to recognize before directly translating X into Z. The Y is having the more part. Now the Y is handling a machine M and machine code M. Okay, such machines, because this Y, these two are only. The machine language and the target machines are nothing but both are equal. Okay, it may be completely optimized or semi-optimized. Such machines as compilers we are calling it as YMM. At the outset, we are calling XYZ source, implementation language, destination language. In the intermediate, we are identifying the intermediate the language M, okay, and target machine code. So if you want to execute that XYZ using YMM, then we'll get a compiler. Then that means if you are adding these two particular thing, finally X and Z. X is the source. The middle M is representing now this intermediate compiler YMM. Okay. So finally we are getting XMZ. Okay. The source language is intermediately converted into machine language M. The source language Y intermediately converted into intermediate language M. Okay, right. That means the compiler for the source language X, whatever it is generating the target language Z, which runs on the machine M, Now, because the machine now doesn't know the source language or implementation language, it knows only the machine language M. Right. Okay. Now, this particular process we'll see within some examples. Okay, a compiler can be characterized by the three languages. Whatever the previous three slides we identified, it contains a source language, it contains a source language, it contains a target language, it contains an implementation language. This representation can be represented by a small symbol, that can be represented by a small symbol, T-shaped symbol, or we can call it as a T diagram. Shows a compiler which is taking source language and developing the target language using the implementation language. This is the representation of the compiler, source language, target language, implementation language. Okay, right. Now, so following some steps to produce the new language L for the machine A, in the intermediate stages, we are representing for that particular compiler, source language, okay, or in the target machine A, implementation machine language A. That it is represented using this particular thing. It is a subset, not final one, because intermediate. We can call it as a subset of the compiler. The subset of the compiler, we are representing C as a capital letter S, of course, the shape. Okay, SAA is representing source language, whatever it is taken from the previous phrase, and it is the target machine. The implementation target machine language. These two are now machine related. Okay, S of the desired language. Okay, using the language A, the machine language A for the compiler, which is running on the machine A, and that related machine language A, because that is the thing. Okay, right. So this particular things compiler, we can also create a compiler of the even using this particular source language L written in the subset of the L. Okay, and can be the machine code A. Okay, the language L, whatever we are using the language in between, also create a compiler. It can take the language L source language. We are having the implementation language for the target machine A, for the target machine A. Okay, right. We get right. The thing is now we are having the two different languages now, because finally we need to convert into the target language machine, that A. Definitely that whatever the machine we are implementing the target code, that language must be A. Whatever the language from the previous phases we are taking, it is L. Okay, let this particular part is the final part. Similarly, we are having the part from the source language. Okay, from the source language. Okay, that L is from the previous part. A is for the machine A, whatever the machine we are going to generate, and the source language, that particular implementation language is S. Here we can identify in the intermediate the bootstrapping compiler or cross compiler, whatever we are generating. This the previous stage implementation language must be the previous parts implementation language must be input language here. Previous stages, okay, implementation language is going to be source language for this particular cross compiler or bootstrapping. Similarly, whatever the target code, it is going to be generated as target machine code, okay, must be implementation language for the next target, must be implementation language for the next stage. That is the thing we need to observe here. Okay, we are having such a sequence of cross compilers more, but whatever the thing is, whatever we are identifying is in the previous compiler stage, source translation language, okay, implementation language, implement here it is implementation language must be source language for this cross compiler. We are talking about only this particular part. For it we are having the input, the previous stage is this, next stage is this. For this particular part, previous stages implementation language must be source language for this particular part. Similarly, whatever the it is implementing the target code, machine related code using the maybe say machine language, must be implementation language for the next part also. Okay, right. That means it is generating a language in some form. That language must be understood by the that other next parts implementation language. Okay, this is called as cross compiler. This is called as cross compiler. Okay, once again we can implement the whatever I explained in the previous slide once again with the this particular slide. Okay, so we are creating compiler of many different forms. Particularly here, similarly we are having one more thing, XYZ source target, but only for this particular part, implementation language, X machine language, and the final machine code. Okay, is joined with the cross compiler YMM. Okay, for the machine, whatever the target machine code for the particular machine language implementation language. Okay, these two must be when you are joining two compilers parts with the other compiler part, these two must be the same languages. These two must be the same languages. Okay. Now, right. That means this XYZ is implementing some part of the translation. This YMM is handling some part of the compilation. So finally, we are getting XMZ is another part of the compilation. Okay. So here XZ is common. Here also we are treating XZ is the common, but here intermediate translation languages are changing. Intermediate translation languages are changing. We are starting with the implementation language Y, and slowly we are moving into the machine related language. Machine related language. Okay, right. So if you are identifying into the particular small steps, the compiler takes C language and generates an assembly language as the output. The availability of the machine of the assembly language we are treating. First, we are writing compiler for small of the C assembly language. That means we are not directly converting into the machine language. First, the C language is converting into the assembly language of the related machine using the assembly language program as implementation language. Then this particular the thing is we are handling with the other source program C language. So a small set of C. Okay. we are dividing into the particular thing as compiler 2. Then finally, we are joining these two with another cross compiler. Okay, the using in this particular fashion. We are joining these two compilers, compiler 1 and the compiler 2, together for getting the final output. This is the compiler 1. In the first stage, we are identifying this is the uh, next part of the compiler. That means optimizing the nothing but optimizing the your machine code or target code like this particular thing can be done by another part of the compiler. Okay, so this particular part we can treat. Okay, this is the initial part of generating the target code. Okay, this can be identified uh, optimizing the target code, and finally it is generating the required uh, machine code case. Okay, right. So this is this particular translation process is called as bootstrapping. Translation process is called as bootstrapping. We can see all this as maybe pass one. We can call it as a pass two. Similarly, we can have n number of passes. Similarly, we can have n number of passes also. This process of implementing the compilers is called as bootstrapping process or bootstrapping